Thank you very much for this very, very kind introduction. Yeah, I don't know that was the person you were talking about me, but very, very nice and kind. So in order to get you the right impression, I think it was a good idea just to start with an error, just a typo on the first slide. Anyone spotting it? It's the date, yeah. Because I was told it was a good idea to start a talk with a joke here, and I only have one, and then you scheduled my talk and it doesn't work out anymore. Yeah, because my idea was, I just wanted you to thank for this very awful date in scheduling me. Yeah? Look at this date, it's 23, 23, 20, okay, it's a reverse 20, and I really like it. And I even have attached my number of slides to it, yeah? So 20 plus 23 is 43, yeah? So, yeah, but now I cannot thank you for that, so I really honestly thank you for inviting me. It's a great pleasure, very nice place. So let's start. Yeah, so let me start with the introduction. The most important thing, yeah, people I've been working with. So it's Daniel, a former PhD student of mine, Michael, Teresa and Alfred from Bayreuth. Many greetings from Alfred. Unfortunately, he cannot come here. He planned to, but it wasn't possible. Teresa is my current PhD student. She will give a talk on Wednesday. There's Sam and then Thomas. And of course, there's a nicer way to introduce them. Yeah. So here are they, all of them. Yeah, and some dots in between. Okay. So yeah, let's start with the preliminaries. I want to talk about codes. And just to keep it very general, what is a code? It's just some subset of some large universe, and we have a distance function on it, just to measure distances between those elements, and this is a metric. Unfortunately, I cannot be that general, so I have to slightly change it. Yeah, it's also a code and a metric, but now I assume that the metric is mapping into the natural numbers, not real numbers, but integers. And once I have it, then I can speak of a divisible code. And what is a divisible code? Just some set of objects given some distance function, and whenever the pairwise distances are divisible by some number delta, this code is called delta divisible. Yeah? So therefore I need integers instead of real numbers, so otherwise it wouldn't make sense. Okay, this of course can be studied in different metrics. Yeah, someone is laughing. Yeah. It can be studied in the rank metric. That's been done by Olga, Paolo, John, and Ferdinando. And if you have any questions about this, just ask the guy. Just laughing, yeah? Ferdinando's here. And it's really an interesting question in different metrics, and you can study different things. Today I just want to talk about the Hamming metric. And it was nicely introduced earlier on. What is the Hamming distance between just the number of differing symbols of a finite field? So let's start with linear code. So I will specialize to more and more. I just look at linear codes. What is an NKQ code? It's a k-dimensional subvector space of some vector space fq to the n. Q is the prime power, just over some finite field. Small example. 732 simplex code. Yeah. Code words of length 7, just binary integers, 3-dimensional. Usually started or written down in terms of a generator matrix. Yeah? So all vectors we can get by linear combinations get me this code. Yeah, I like the geometric point of view much more. And I want to introduce it now. So how does it work? Once you are given such a generator matrix, you can look at every column and consider the one-dimensional space spanned by it. In the geometrical sense, this is a point in the projective geometry. And so a code is also a set or multi-set of points in projective spaces. And this is the way I want to look at it. In that setting, code words correspond to hyperplanes. So yeah, you can assign to each code word geometrically a hyperplane, or if you like the geometry more, just talk about hyperplanes and not code words. And how does it work? Hamming weight of a code word is very much the same as the number of points that are not contained in the corresponding hyperplane. Yeah, so it's about intersections between hyperplanes and points. And I really use these geometric notions when I speak of one-dimensional spaces, two-dimensional, and so on. I speak of point, one-dimensional, line, two-dimensional, a plane, three-dimensional, hyperplane, dimension one less than the dimension of the ambient space. As sometimes said, Z of points. Actually, we have to talk about multi-set of points because in a linear code we can have repeated columns or columns like over F3 that are multiplied by 2, and so the points are the same. So a multi-set for me is just a mapping from the set of points into the integer. It's the multiplicity, yeah? So the number of times it occurs as a column in such a code. Let's restate this simple definition of a delta divisible linear code geometrically. So a multi-set of points corresponding to a linear code is called delta divisible if its cardinality, so the number of points counted with multiplicity, is concurrent to the multiplicity of each hyperplane, modulo this delta. Okay, this sounds a bit curious to state it like that way, but it's a very natural definition because it just says a multi-set of points is delta divisible if its corresponding linear code is. Yeah, and it's just like taking this multiplicity of the hyperplane to the other side, and you are just counting points not inside the hyperplane. Okay, so simple object. Let's do the basic stuff. Consider some k-space or k-dimensional space and counting points. It's a counting number of possible vectors that are non-zero, and we have this thing that you can multiply with an element from FQ, and you get the same point because we are only interested in the one-dimensional subspaces. So this number is then given by q to the k minus 1 over q minus 1. Okay, so now geometry helps. Consider a k-space, just a k-dimensional space and some hyperplane. How can this k-dimensional space and this hyperplane can intersect? The k-dimensional hyperplane can be completely contained in this, the k-dimensional space can be completely contained in this hyperplane, or it intersects in dimension k minus 1. Okay, then we can count the number of points, so two possibilities, k over 1, q binomial coefficient, or k minus 1 over 1, q binomial coefficient. And you can see the difference is a number that is divisible by q to the k minus 1. Yeah? And that's almost it. If you're looking at the characteristic function of such a k-dimensional space, so all points contained in that space give you a 1 and the other ones have multiplicity 0, this thing is q to the k minus 1 divisible, just by the geometric fact that we have dimension. Yeah? Its intersection is in dimension. And this directly implies the most useful result, I would say, in the Z area that makes it interesting to study this thing. Assume that you have some multi-set of subspaces, U1 numbered up to UL, and assume that their dimensions can be arbitrary but lower bounded by k. So each of these spaces have a dimension of at least k. This also gives you a multi-set of points, just summing up their characteristic functions of those objects. And this again is q to the k minus 1 divisible, because every object is, and by adding it, divisibility won't disappear. Next lemma, you can also go over to the complement. Yeah, so say, okay, you had a lot of these subspaces, all of them having dimension at least q, so multi-set of points corresponding to it is q to the k minus 1 divisible. And now assume some kind of a complement. So assume that every point has a multiplicity of at most, say, lambda. And now you revert things, go to every point and say, okay, multiplicity now is this lambda minus the original multiplicity. Yeah, so if it is a set, and set of points, and you have this lambda equals to 1, then you have just the complementary points. And now, yeah, the entire ambient space is, of course, a subspace. It is q to the k minus 1 divisible, and so the complement is also, because I'm just choosing one characteristic function that is q to the k minus 1 divisible minus some other characteristic functions that are 2. Yeah, and that's it. So it even was the entire proof. Nothing more inside it. Yeah, so very, very deep things, as you see. So completely simple and almost trivial. But these observations have many applications. They have applications in vector space partitions, partial spreads, packing problems, covering problems, subspace codes, and I want to show you it. Yeah? So you have done the hard part. We will come to the applications in the end. So yeah, let's start to get an idea what applications are by a very, very concrete example. Yeah, some of you have seen this. So it's still the same example, so you know the answer. Yeah, question, geometric one. Can we pack 20 solids? So this is 4-dimensional subspaces. If you like binary vectors, each of them consists of 15 vectors, yeah, spanning a 4-dimensional space. And 30 planes. So 30 3-dimensional objects, each of them consisting of 7 points. In F2 to the 9. Yeah? Packing means put them into that space so that they pairwise do not overlap, except the 0 vector, which is not a point geometrically. Okay, yeah, is it possible? Yeah, first thing, counting points. I said a solid has 15 points, plane has 30 points, F2 to the 9 has 511 points, and counting tells you, okay, yeah, it may be possible. We even have 1 point over, yeah? So you can cover all points except 1. So why shouldn't this thing exist? Not exist. But the answer is it does not exist. Because, I told you before, when we have multi-set of subspaces, assume here we have solids and planes. Dimension of them is at least 3. So this thing should be q. Q now is binary case, it's 2. Q to the k minus 1 divisible. So 2 to the power of 2 is 4. So this should be 4 divisible, this multi-set of points. Also the complement, yeah? So this single point should correspond to a linear code that is 4 divisible. Okay, we have a linear code of length 1. Every code word should have a weight divisible by 4. Clearly this is impossible, yeah? So this geometric object does not exist. Yeah, and it has a very simple proof. Okay, that's what it's all about. Yeah, in general, you can look at the generalization of this question. You can speak about vector space partitions. What is a vector space partition? A vector space partition is just a collection of subspaces, pairwise non-intersecting, yeah, partitioning the set of points, you can say. Yeah, they come with a type. It's just the distribution of the dimensions. Yeah? For every dimension, you say how many times they appear. So in our example, it's type 4 to the 20 solids, and 3 to the 30 planes. Yeah. And if you are not so keen on partitioning, because it was a packing problem, simple thing is just add the uncovered points. Yeah? Here it was 1, so 1 to the 1. In this situation, you can play the same trick. Okay, those things give you some divisible set, some divisible code. You can go over to the complement, and you also get a divisible code. And here, for vector space partition, maximum point multiplicity is 1, so you get a projective code. And we will come to that later on. So maximum column multiplicity 1. This also fits into the geometrical setting of partial k-spreads. Partial k-spread is a collection of k-dimensional subspaces pairwise non-intersecting. Yeah? Same trick, add the number of uncovered points as points of dimension 1, and then you have a vector space partition. Yeah? So there you can apply that too. So far, so good. Of course, when you look at projective spaces, you can also look at affine spaces and talk about vector space partitions there, and can use similar results on divisible codes. Yeah, this was some kind of an introduction. Let's get to some results. And maybe, first of all, to be honest, it wasn't me who introduced divisible codes. They were studied a long time ago, and they were introduced by Howard Ward. And he has done a lot of things on it, and here's just a collection of some of his works on this. And this is really actually old stuff, and now only renewed due to its application with subspaces, collections of subspaces and stuff like that, and extended to other metrics. So, yeah, to come to one point. Yeah, suppose you have just some multi-set of point, completely arbitrary. You have some divisibility, let's say it's delta prime divisible. In the geometric setting, it's pretty easy. Take the multiplicity of every point and just multiply it by some integer lambda. What turns out? You get a lambda times delta prime divisible multi-set of point. Yeah? Nothing about it. It's a pretty easy calculus, and behind that is, of course, the characteristic functions working, how you are describing those things. Okay, in terms of codes, these are repetition codes. Yeah? That's a pretty trivial construction. Yeah, so. First thing, do divisible codes exist? Answer is yes. Take anything you want and then multiply it by your constant delta. Yeah? So you have divisible codes for every constant delta, yeah? But just starting from anything and then just taking the repetition code of it. Yeah? Nothing interesting to talk about. And this interesting thing was done by Ward. It also works somehow in the other direction, only somehow. His theorem is, okay, assume that C is a delta divisible code over FQ as some divisor of this delta, and assume that it is co-prime to the field size. Yeah? So maybe say, okay, it is a 12 divisible linear code over the binary field. Yeah? So this S would be, say, 3. 3 divides this 12, but is co-prime to the field size. Okay, and then the theorem tells you, okay, if that is the case, then this code actually is a repetition code of something else. Yeah, you can factor out this factor S that is co-prime to the field size, and he showed it has to be a repetition code, yeah, for this thing. So, what does it tell us? So, in our situations, if we put away the trivial things, we should only be interested in divisors delta, yeah, that are powers of the characteristic of the field. Yeah, so okay, it's a little bit more complicated. I cannot say just field size, because when we are over F8, there may be 2 divisible codes, 4 divisible codes, which are not repetition codes. Yeah, so this divisibility constant will always be a power of the characteristic of the field. And then for other things, we can always apply this theorem of Ward. Yeah. So, yeah, one thing is, of course, first thing is, I showed you, okay, those codes exist for every field size, for every divisibility constant. Let's make it a bit finer and say, okay, what happens if I prescribe the length? Like before, and in our application, I asked you, is there a 4 divisible binary linear code of length 1? This was the point, this thing does not exist, and so this geometric configuration of the solids and planes does not exist. And there we specified length 1, yeah, because 4 divisible linear code exists, of course. Yeah, just take a point and a 4-fold point. Yeah, repeat it 4 times, it is 4 divisible. So we need more information, and 1 is the length. Okay, good news is there is a complete classification. If you tell me some length, field size, and some divisibility, I can tell you, okay, a linear code with those parameters exist or does not exist. And this is this characterization result. Yeah, it's a bit funny. It's some case of a number system, but I won't tell you any details because these will be told to you by Teresa Körner. So look forward to that on Wednesday. Information really is, you can actually decide it by a very simple algorithm. Yeah, if those things exist. Okay, and you can also look it up in the paper, of course, if you want to. So, yeah. So, just to be honest, I would say it's a cool result, it's a complete characterization, but it has a lot of blind spots. Yeah, it seems so complete, but it is not. Yeah, so length of a linear code is just one key parameter. Maybe we have more. One thing is maximum point multiplicity. Yeah, which is important for the case of partial spreads. Yeah, maximum point multiplicity is 1, and there's a difference if linear codes exist or if they have to be projective, because then I can't play this thing with duplicating columns. This doesn't work anymore. And okay, so yeah, the second bullet, projective code, maximum point multiplicity 1. You're also interested in characterizing possible lengths given some divisibility. What I can tell you is this is widely open. You can do a lot of things there. The more general thing, you have just some upper bound on the point multiplicity. Also mostly open and will be covered in a talk by Teresa. Yeah. Hidden in the technicalities above, I said, okay, given some length, does there exist a q to the r divisible linear code with those parameters? Sounds pretty general, and my assumption was r has to be an integer. And when q is 8, there's also 2 divisible and 4 divisible, and it's not covered by that theorem. So this is also open, but there's work in progress. And yeah, I'm pretty sure you can assume further coding theoretic invariants that can come into play and affect this thing if they exist or not. Okay, so yeah, let's come to this important thing because of the application of partial spread and vector space partitions. So maximum point multiplicity of 1, so projective codes. Yeah, so to repeat, partial K-spread is yeah, just some set of k-dimensional subspaces pairwise non-intersecting. Translated to vector space partitions, only occurring dimensions are k. We have here mk of them, and there are some uncovered points. Here number is m1. In that language, they call those uncovered point holes because they are not covered. So you can say the set of holes of a partial spread forms a q to the k minus 1 divisible projective code. So directly concluded, as I've shown you on the first slide, by the simple observation of this divisibility. But now we have this extra condition that the linear codes have to be projective. So again, this is also not covered at all by this theorem. In my application, this doesn't matter. Yeah? When you think of these 20 solids and 13 planes, there was no 4 divisible linear code of length 1. No matter if it's projective or not. But there are cases where this makes a difference, where linear codes exist that have the right divisibility, but they are not projective. Yeah? So you can get something out of that. So just as an information why this should be interesting, if you are interested in the geometrical things of partial spreads. For partial spreads, one problem is to get the maximum possible cardinality. Yeah? So how many k-spaces can I pack into fq to the n without pairwise overlapping? And you get some upper bounds on that, yeah? How many you can get. And information is, there are a lot of results in the literature on upper bounds of partial splats, and all of them so far can be concluded from non-existence results for projective Q to the k minus 1 divisible linear codes. So once you have that, you get all of the other results mentioned so far in the literature over a long time period. And yeah, how do those results look like? You specify field size. Here I took the binary field. You specify a divisibility. Yeah. I remind you, it has to be a power of the characteristic of the field. So now it's 2. So possibilities are 2, 4, 8, 16, and so on. And then you want to know which lengths are possible, yeah, for, say, 2 divisible binary linear code. We've used the fact that 1 is impossible, 2 is impossible, and anything else is possible. Also, for 4 divisibility, you get a complete characterization. 7 is possible. Yeah, and here's a chance to look at the geometric thing again. It's not a complicated code. You can just take a plane. 3-dimensional space consists of 7 points, is 4 divisible, because every hyperplane intersects in either a line, 3 points, or the entire plane, 7 points. So modulo 4, it's all the same. 8 is possible, and then anything going on up from 14 is possible. All other cases are not possible. Divisibility 8 was also done. Here we have a lot of cases. Some small examples. 15, 16, 30, and so on. A lot of gaps. 52 is not occurring. 53, 59, and starting up from 60, everything is possible. Yeah? So if you say, okay, I want to have does there exist a projective linear code 8 divisible of length 78? It is existing. Yeah. So, okay. Okay. Open problems, of course. After 8 comes 16. What's happening there? Yeah, I don't know. Only partial results are known. Maybe even more interesting is the case of larger field sizes. What's happening there? Almost nothing is known. Yeah, not much. And one application, as I told you, are upper bounds for partial spreads. You can use that there too. Okay, now I want to dive a bit into the details, how this game is played and what is needed, what further research is needed. It comes in several parts to obtain such classification results. Just an advertisement, non-existence results. If you can show that some code of certain parameters does not exist at all, it has implications. So this is just an example of mine. For one specific setting, length 131, our binary fields, and 16 divisibility. Yeah, so one of those cases not covered here for a certain reason. I was able to show such a code does not exist. And it gave me an entire paper. And so why is that interesting, that it does not exist? Because implication is, in F2 to the 13, you cannot have 260 5-dimensional spaces pairwise non-intersecting. It's not possible. Yeah, and the only reason I know so far why this thing does not exist is showing that there is no 16 divisible binary linear code of length 131. Yeah, and you can go on like this. Maybe this is interesting from a different perspective. Maybe the older ones of you know there was a period where it was somehow hot topic to exclude the existence of linear codes of certain parameters. Yeah, some of you still know it is still. Sorry. Yeah, you know, of course, yeah, because when you're interested in optimal linear codes, you want to know, does such a code having this minimum distance, this length, and this dimension exist, yes or no? Yeah, and this was the main problem of coding theory, if those things exist. Yeah, I learned it got a bit down, and it's not completely interesting anymore if you submit something like this to IEEE transactions on information theory. They tell you, oh, well, interesting, but you are 20 years late. Ne? Yeah. Now people are doing different things. But now's your chance if you're good at this. Just don't do it for distance optimal codes, do it for divisible codes. Very same methods you ever done before, everything you learned, we can of course apply it here, and we need it here. Yeah, what do we need is, of course, famous McWilliams identities. Yeah, just counting linear programming, integer linear programming, more insights, getting more inequalities for some reasons that you have. So if you know that, this is a good way to go into it, and I would say it is interesting. And there are some parameters that want to be settled, and you need all of that what has been used and done before in a slightly different setup, focusing on a different parameter. Okay, so yeah, just to give you a glimpse what this is. So this McWilliams identities are of course the start of everything for this non-existence proof. But you can go beyond that. Yeah, what can we say? Yeah, maybe phrase it differently. Start with a simple example. Assume that you have a binary linear code, and you know each weight is 4, say. Yeah? All the system, the same weights, and the famous insight, these are simplex codes. Yeah? Once a linear code has only one weight, it is a repetition of a simplex code. Yeah? Okay, something different here. So, what is the setting? We have some integer delta, and we assume that, yeah, this is technical. Just assume that delta is q to this something, just the power of the field size, yeah, to make it easy. And so, maybe just talk about, make an example, 8 divisible linear codes over the binary case. What you can do, given a huge code, you can choose all code words of, say, weight 8. Yeah? So having the minimal weight. And taking these, they generate a subcode. So you have a subcode of this larger code, and here in this language I say it is spanned by the code words of minimal weight. Yeah, and maybe it is interesting to characterize the structure of those subcodes. Yeah, it's like, say, what is the structure of the even codes in the 4 divisible code words? And you can answer is, you can characterize them. Those subcodes are just concatenation of some possibilities. And first thing is simplex codes. Of course, they are a possibility because they have divisibility. So those technical parameters are just there to attach the right divisibility. Just ignore them. Yeah? So it's simplex codes. First order Reed-Muller codes pop up in the binary case. And in general they pop up. And repetitions of binary check codes. And point is, that's all. That's really all that can happen. Yeah? If you are taking a general Q to the R divisible linear codes, you pick all code words of minimum weight, which matches the divisibility here now. And it's only working if the divisibility matches the minimum weight of that code. Then you can completely describe the structure of those codes, of those subcodes. And these are just a few possibilities. Yeah? So in a way, it's an extension of this famous result that if you have just one weight, it's repetition of a simplex code. Just to give you an example what you can do with that. So this is just a finite list of possibilities. You can just loop over all possible combinations of that, taking several of these. And what you get is, yeah, in terms of the McWilliams identities. So here in our example, I'm looking at 8 divisible linear codes, prescribing the weights to say 8, 16, 24, which of course limits how often I can take a simplex code and so on. Not many numbers can occur for the number of code words of weight 8. Yeah? So this is just a finite list, in some cases are just excluded. So this is a top-on the McWilliams identities. Yeah? You get more information because you have the subcodes and everything which has a minimum weight is covered there. Okay, just as an example, we won't use these specific numbers. You can do things like that, and most surely you can also do different things in other situations. Yeah, this is another thing I want to show you, which maybe is not so common. Subwords of code words with a higher divisibility. Yeah, so same game, assume you want to look at an 8 divisible linear code. Some code words might have a divisibility by 16. You can look at the structure of that, and maybe you can say something about it. How many code words there are, I don't know. Okay, so setting is here for the binary case, you assume that, let's make a very simple example written down here. So just consider an arbitrary binary linear code. Look at the code words of even weight. Say form a subcode. Yeah? And so, and in terms of numbers, there are just 2 possibilities. Yeah? It's half of the code or the entire code. So it's 2 to the k minus 1 or 2 to the k. And this is actually a simplest example and a longer list done by Gürtmann and Simonis. So assume you have an, let's just consider the binary case and NK decode all weights divisible by some parameter delta, that is a power of 2 here. And yeah, some technical parameters, just ignore it. What is important is the things highlighted, this parameter t. It's summing up the counts of all code words that have a higher divisibility, yeah, are divisible by 2 delta. Yeah, just some number. In the example before, we had precisely 2 values for this t that are possible. Now it is a bit more complicated. Yeah? You have some information about the divisibility of this t. This is part 1. Part 2 is, yeah, under a certain condition, you can say this number is exactly 1 depending on another parameter, and something similar for a certain range of parameters in number 3. Yeah, so you get also more information on the McWilliams identities, yeah, in that setting. So this is a useful thing. And maybe interesting, that steams from, it steams from investigations of generalized Reed-Muller codes. Yeah, if you have information on the possible sizes, on the possible weights of a Reed-Muller code, you get such results. Yeah? And so I just put it down here for the binary case because there are many open problems yeah. And any new result there gives you results here that you can use for the non-existence of code. Yeah? So I want to make an advertisement for that. This is really cool stuff, and if you have any new results here, they are quite useful. Okay, so yeah, maybe you don't like this non-existent thing because it's a typical mathematical thing. Something does not exist. Yeah, who cares? Yeah, mathematicians do, and it's important, and it's the hard stuff. But maybe the more fun stuff is we also need constructions. Yeah, we need constructions for those things because when we want to have a complete classification, we want to know those things exist and those things don't exist. So first step maybe is constructions. And yeah, just to show you something. If you like geometry, ovoids are nice objects in projective geometry. Yeah, like almost always. Whatever you're talking about, take some nice geometric object. Most likely it is an example, and here it is too. Yeah, so an ovoid is a set of q plus 1 points, and yeah, it's q divisible. Small thing, and you need that thing. Yeah, so of course, geometry is a source of constructions. Another thing I would call a cones construction. Yeah, what do you do? Just pick some base of a cone, some, I don't know, how do they use, some vertex x, yeah. Just choose multi-set of points that have some certain divisibility. No? So I don't know, one here, one here, one here. What you're doing is you're connecting all of those points with this base, so forming your larger subspaces, and take the union of all of it. And there are some technical things, what you do with the basing below. Use it once, use it not at all. And what it turns out is, in any of these cases, you get some object that has a certain divisibility which is increased, just by a nice geometric way, yeah? Extending, to make it easy, when the base is a point, you have some points in space, you connect it to them, then you have a set of lines leaving off the base, and this gives you something that has a certain divisibility, yeah? So, do not matter about the technical details, idea is pretty easy, yeah? And it works like that to get those things. Yeah, switching construction. Maybe put it that way. As an example for the binary case, consider some multi-set of points containing several disjoint lines. What you can do is take such a line, consider an arbitrary plane through that line, remove that line and take the remaining part of that plane. Divisibility, if it was 4 before, remains 4 before. Yeah? So I would say in a way it's switching out a line against the affine plane. Yeah? And in this situation I remove 3 points, I get 4 new points. By the switching operation I can increase the length by 1. If my object has many pairwise disjoint lines, I can get a whole range of parameters this way. And this is what is written down as a corollary. Yeah? So for a certain range of parameters, there exist projective divisible codes just by such a simple idea. Yeah? And it also works for larger field sizes, but then you have to say remove one plane, but you have to replace it by q minus 1 affine planes. Yeah? So for q2 it's simple, it's 1, and larger field sizes it's more of them. So it's not so completely nicey to get all of them. Yeah, so, okay. And nothing of this, I would say, is impressive. It's just to provoke you to come up with more sophisticated constructions of projective linear codes, because I guess there are a lot of them there, especially if you look at larger field sizes, not the binary case. So yeah, in the binary case, you can do a lot of this computer searches and found most things that you find interesting. When Q is getting larger, as said before, you need mathematics. Yeah? So when you can't do a exhaustive search anymore. So what is the connection with all of this? So yeah. Let me talk about the Frobenius coin problem or the chicken McNuggets problem. And of course, I have to use this number 43 again, yeah, just to make this talk round. So, yeah, consider McDonald's in the UK. At least some time ago, they sold chicken McNuggets just in packs of 6, 9, and 20. Yeah, so, of course, if you want to have 7 chicken McNuggets, one solution might be buy 9, spend 2 to somebody you like or don't like, yeah, depending on your taste. But now look at it mathematically. Yeah, say okay, spending or wasting is not allowed. So, is it possible to buy 7 chicken McNuggets in the UK at McDonald's? And says no, either 6, 9, or 20. But of course you can combine. Yeah, so 15 is also possible because 6 plus 9 is 15. Yeah, going along with 6 and 9. You can reach anything that is divisible by 3, maybe. If it's not divisible by 3, it's not possible. But we have 20 anyway. Yeah? So, okay. And what is this thing with this 43? 43 is the largest number of chicken McNuggets that you cannot order in McDonald's in the UK if you stick to this number 6, 9, and 20. every other number is possible. Yeah? So if you say me 75, it will take a few hours, but then I can give you an answer. There's a linear combination of 6, 9, and 20, how to get you to 75 was my example. Yeah, I think so. 43, you can check, is not possible. Okay, and there's one geometric solution to that problem. If you have two integers, a and b, co-prime to each other, largest number that you cannot express as a integer linear combination of these a's and b's is a times b minus a minus b. Yeah? And if you have more of them, so 3, like in our example, it gets more complicated. And later on, there are no complete analytical solutions. So this is open. But how does this fit into my problem of the classification of possible lengths? Yeah. Okay, and the idea is, clever guys come up with some constructions for those, say, projective delta divisible linear codes or whatever your parameters are. And then, of course, you can combine them with these pluses, because if I have a delta divisible multiset of points here, another one here, just take the union. So if I can have length A and length B, I can also have length A plus B. Yeah, so we are just in the setting here. So this is the answer why I can maybe go back to this, to those results. Projective 2, 4, and 8 divisible binary linear codes. And in the end, it was always possible if this n is large enough. And all you need to do is to have just some base examples. And if their length doesn't have a common factor, you get that for free. Yeah? So it's always a finite problem. You just need to have some good base examples and then to look up what's happening. Okay, so this is just to explain to you the rules of the game that I want to play there. It's just base examples are almost done. These are leaving over some parameters. Okay, if you're keen on non-existence results, you can try to kick them off or to find further other examples, and then you have settled such a complete classification. Yeah. Okay. So that's it. Yeah. One different application. It's say classification results. And this is in the world of partial spreads also interesting. When you say, okay, in some cases you have a spread, that is set of k-spaces that every point is covered, a complete partition. And then you say, okay, well, what is happening? What is happening if I remove one of them? Yeah, so say, partial spread not of maximum size, can it be extended to a thing? Yeah, like we have in coding theory, can we extend linear codes? Can we extend partial spreads? And here, answer is yeah, if you do not deviate too much from the spread situation, then you can always extend. Yeah? If you say, just make an example. Start from a line spread and say, okay, you remove 2 lines and you have a code with certain parameters. Then you can ask, can it always, in the geometrical setting, can it always extend it to a spread, or can it not? Yeah? And those results tells you, okay, for certain parameters, you have to. Yeah? It can be always extended. And it comes a bit technical. Yeah? I will translate it, what it means. Just make an example. Say we have 8 divisible binary linear code of length 30. What are those numbers about? 8 divisible linear code you can get from a solid. Yeah, that's the most easy example, has 15. Yeah, so of course you can get 13. You can just take 2 solids, and that's it. But question is this all? Or are there other constructions? Yeah, saying, okay, I want to have length 30, I want to have divisibility 8, classify them. Yeah? And here the answer is, for certain ranges, it is just a collection of unions of those spaces. And if that is the case, this naturally gives you this extension thing, because these are the holes, uncovered points in this thing, and they form subspaces. Yeah, then I take those subspaces and I have this extension. Yeah, so this is how it is working, and so we are also interested in the classification results, because classification results give us those extendability results. Yeah, once we know it has to be a union of those nice objects, then I can use those as an extension. And in some parameters, other things occur. In the setting, they used blocking sets, and you get quite general bounds for that. Done. Blockhuis et al. A lot of names should have popped up here. Yeah, so many work done on blocking sets. So, similar thing. If you're starting over FQ with Q lines through a common point P, take the union of all of those lines, but remove the point P. This thing, some call it a cylinder, because it's parallel lines in the affine space, so something you may call a cylinder. Point is, this is a Q divisible point set, because you can check either you contain the entire line or a point of it, and how is it with the intersection with this point P or not. And every line has to intersect this. So just technical, but it can be done. It can be easily seen. This construction in general gives you a Q divisible point set of cardinality Q squared, those cylinders. And natural question now is, what about the opposite? Does every point set or projective linear code with those parameters stem from this construction? So is it a cylinder, geometrically speaking? Answer is yes, for a few cases, 2, 3, 4, 5, 7, but no for 8. So maybe those of you who are interested in geometry, 8 is a prime power, but it's not a prime. Maybe something more geometry pop up there. Yeah, it is like that. And there are papers on that studying those things, and it's interesting stuff. And I have no clue what's going up in general. So the conjecture is, at least for Q being a prime, there is nothing else. This is called a cylinder conjecture. Coming from a completely different area, but just reformulated in the language of divisible codes. But it's then the same. Okay, so almost everything is open. So there's also a lot of stuff to do. So we've done pretty well. Now I do my promised applications. So maybe the most interesting part. So subspace packings and coverings. What is that? Any problem you have, say, okay, I have some set or multi-set of subspaces with certain dimensions, whatever, and I want to pack it into another subspace. Or the corresponding covering problem, I want to cover all points from this subspace with all other subspaces. Relax. My lemma again, you get this set or the complement is a divisible set. For those problems, you can use those characterization results for possible lengths of divisible codes. Subspace codes. Okay, what is a subspace codes? It is also a collection of subspaces, but the dimension of the intersections are restricted. That's more or less the point. And you can claim it, of course, in subspace distance and speak all of those coding theory language, but geometrically, intersection is restricted. Idea of the Johnson bound was consider a point, consider all code words through that point, factoring out this point, I get another object, another subspace code. How many of them can there be? In our language, this is upper bound and the maximum point multiplicity. So this is a classical Johnson bound, and now sharpening of the rounding. You can the very same trick. You can say, okay, it's about covering of points. So each point can be covered at most this and that time. I look at the holes, what is missing. This also has a certain divisibility. You look at those length results, and this gives you better bounds. In a nutshell, it's just this rounding down to integers is a bit sharpened. And here again, information is at least the known upper bounds for subspace codes that I know all stem from this thing, except for two cases that were done with heavy computations using integer linear programming. Exact the partial spread cells. So this might be interesting. Our bounds are weak anyway. but so far we do nothing better, and it's stemming from here. Yeah, distance optimal codes, I've talked about it a bit. The other thing is, we have a result of war telling you whenever you're looking at distance optimal codes, in some cases you get divisibility for free from theory. So it's also connected there. If you're interested in few weight codes, so codes with few weights, and now applications in cryptography and everywhere, and my point of view is, okay, if you look at those examples, in many cases, they are divisible codes. So they give examples for that. Yeah, you can look up and send me all the results, and maybe you got lucky and have a hit. And in the other direction, yeah, a divisible linear code is a few weight code because the divisibility kicks out many of its weights. Yeah, so it works maybe in both directions. Okay, yeah. Group divisible designs, if you know of that. I won't go into details. It's a Q analog of a design, and it's also a thing with subspaces and messing around. I would say information from that is whenever you have something with subspaces in some way, look if you can use divisible codes. Mostly likely it will pop up, and what you need is only the two lemmas I put on my first two slides. If it's a multi-set of some points, some restricted upper bound on point multiplicity or something like that, it's most likely that you get results on that and you get extra conditions. Extendability results, just I talked a bit about it just as a highlight. Maybe some of you know Q analog of the Fano plane. It is an open problem if 281 planes exist and if 2 to the 7 pairs intersecting and at most align. And no one knows if it exists or not. From the constructive bound, we have pretty poor bounds. We can construct jet code far away from the 281. Using divisible codes, you can show something else. You can show, if you have such a thing, having 381 planes, then you can always extend it to something like that, to a Q analog of the Fano plane. Yeah, so you also have those extendability results for other objects intersecting in some way. If you're not interested in this stuff, you can play the same game for maximum rank distance codes, because geometrically you can lift them up. You have special point sets with a certain divisibility. Yeah, you also have extendability results for that. Yeah. No details, just to name it. And now a nice picture to come to the end. This is so-called Bart's stick in algebraic geometry, and what is it about? It is about surfaces having many singularities. This is the one attaining the maximum. And what is the point? The point is algebraic geometers have attached linear codes to those objects, and some of those bounds have been shown using coding theory, showing the non-existence of certain linear codes, and you get upper bounds on these geometric objects. Yeah, I see you were standing there. You were looking at my number of slides, getting certainly unrelaxed. So, most important part, this was the talk. This was the title of my talk. So if you take anything alone, that is the title. Relax. Merci pour votre attention.
Thank you so much for this very excellent talk and rich domain and the topics. Okay, any question or comment, please?
Yes, you had a very interesting example with a code with weight 8, 16, and 24, and you want to compute A8. And I was wondering if we should not get the extended Golay as one of these codes.
I guess so, yeah.
So this would be which one of these values?
To be honest, I have no idea.
I don't remember either.
Yeah. But it's a good check if this result can be true. But it should be. Thanks.
Thank you. Yes.
So let's say you fix the divisibility, let's say 5.
Yeah.
Can you construct a code that is 5 divisible code with arbitrary rate goes to 1? Or it's upper bound, the rate is upper bounded by some number?
So far we have not looked at the connection with the minimum distance or something like that, or this is...
No, the rate of the code. I give you 5 divisibility and the rate, I want it as close as possible to 1. Can I go to 1?
No, so far we haven't looked into that. So far we have just focused on the length, but this might be interesting. So this falls into the step looking at certain other parameters. I have done nothing so far and I knew of no result in that direction. Might be interesting.
Thank you.
Okay, thank you.
So you showed some non-existent results for divisible codes. So did you construct any of them? I mean, are they all non-existent results, or do you have some existence constructive methods for divisibility?
Yeah. It goes like...
for
you mean
those
results
ones,
like that, yeah? Okay.
Yeah.
So complete classification. You see some lengths are possible, others are not. Those where they are not, we need non-existence result, yeah? So far away from being constructive. For the positive ones, we need constructive results. So, and it works like this. We need some kind of base examples that we can combine. If I look at this example for 8 divisible, 15, this is a solid. 16, this is an affine 5-space, having 16 points. Then I get 30, 31, and 32 for free, because 30 is 2 times 15, 31 is 15 plus 16, 33 is 16 plus 16. Again, 45 borrowing up to 48, but 49 is again interesting. I cannot get 49 using 15 and 16, so I need a construction for length 49 being 8 divisible. And we have found it, yeah?
And by the way, did you check, partial thread construction and maybe construction of Boolean functions? Did you check their equivalences?
On the set of Boolean functions and APN, almost like that, I'm completely blind. Sorry about that, I haven't checked. Yeah. So maybe there's a lot of stuff hidden there. If you see it is related, we get some objects with a certain divisibility, you may look up if you find something interesting where there are gaps. Here there are no gaps, but I can tell you as the mention said, for field size 5, there are parameters where I don't know if 5 divisible linear codes of that length exist. Yeah, not so large, but I just don't know. Yeah? Neither the example nor the non-existence. Yeah, so yeah, thanks.
Thank you very much. No comment, no question. It's excellent. We have 1 hour for lunch, I think. Okay, thank you so much for this wonderful morning. Yes.
Thanks.